LED, and the design says design a comparator that turns on LED whenever the input voltage piece of S is larger than 2 volts. So we arbitrarily picked some batteries here, 10 volts and minus 10 volts, and the comparator in the operator, we want the LED to turn on when the input voltage is larger than 2 volts, which means when the input is larger than 2 volts, the output, what should the output be when the input is larger than 2 volts?
Output should be 10 volts.
It should be 10. And the way the LED is shown here, the LED appears as a diode, the PN junction, it just has a higher turn-on voltage and emits visible light, depending on the type of LED, when it turns on. So the design here is pretty straightforward. There's our LED, there's our comparator, and our trigger is on the non-inverting input. So the design then basically is how to set the current for the LED. And we'll assume the LED, when the LED is on, its current, but first the op amp itself, let's say the maximum current the op amp can deliver on the output is 15 milliamperes. That's the maximum current it can drive the LED with. And the LED, though, needs to develop have at least 30 milliamperes in order to go to full brightness. So there's a conflict between those two numbers there. So we still go ahead and complete the design of the circuit. So one way you can design this basically says we'll limit the LED. If the LED wants 30 milliamperes, we'll limit the LED maximum current to 50 milliamperes. That would keep from overdriving it. And the LEDs are certainly made of gallium arsenide. It has a forward turn on of 1.5 volts when the LED is on. So the designer decides to go ahead and at least construct the circuit. So if the LED needs 30 milliamperes and it turns on with 1.5 volts across it, we calculate this series resistor is 10 volts. When the comparative output is high, it's 10 volts minus 1.5 volts over 30 milliamps, so it's 283 ohms. And the assumption was made knowing the op amp can only deliver 15 milliamps of current. So this design on paper basically works, but if we tried to build it, it basically would not work because the LED needs at least 15 more milliamps of current, and op amp is limited. So if we keep the op amp, we want to put something in between the LED and the op amp, and this is called a current driver. So we need a device that can deliver extra current to the LED without requiring more current from the op amp, and that's called a current driver. So the first version the engineer decides is to take a NPN transistor and put the LED in the collector and ground the emitter. And then this version we'll call scheme A. So scheme A then is when the op amp output goes high to 10 volts. And we kind of analyze what's going to happen here. When this is 10 volts, what's going to be the voltage on the base of the transistor? It might be RCD. So what will give you the voltage on the base of the transistor?
15 milliamps divided by 10 volts.
Now the
Is it the
now notice the emitter is grounded. Here, 0. So it's a PN junction. So what voltage do we need to turn this PN junction on?
0.7.
0.7. So we need 0.7 volts here. And then we could go to the paper analysis. If the LED needs 30 milliamps, we can probably use I sub C, beta I sub D, calculate a base current, and then calculate the resistor R sub D. So another version is to take the same circuit and put add a resistor in the emitter of the LED, an R sub E resistor. And this is basically called scheme B. And there's nothing obvious in this circuit that makes this preferred compared to the first version. So it is an option. And then the third version is to place the LED in the emitter of the BJT. And again, just based on the configuration, there's nothing really obvious that would say this is preferred over the first two versions. So on paper then, what we would do is you basically have to examine each one. And the first question, can each one of them, the circuits, drive 30 milliamps current to the LED? And after we do the paper analysis, it's yes. They all three will work. And the question of how is just choosing resistor in the circuit and then decide which one of the three is probably the best to keep as the current driver. And then come up with a reason for it. So the first version, this is the scheme A. We can basically assume the op amp output is 10 volts, and we're going to find the base resistor. We have 0.7 volts on the base. Why do we have 8.5 volts on the collector?
VCC minus the voltage drop over the diode?
The LED voltage drop is 1.5 volts, so that's going to limit the collector voltage to 8.5 volts. And assume base emitter is 0.7. And emitter is, because the emitter is grounded, we can get that. And then the lower part here, the collector voltage is 10 minus the LED turn on 1.5, which is 8.5 volts. And we check the active mode collector is 8.5, that's greater than the base of 0.7, and then the base emitter is forward biased with 0.7 volts across it. So the base of the circuit is in the active mode. Now this part here, we can solve for the base current. What we're trying to do is solve for this resistor here. So to get this resistor value, we need to find the current to it. So I sub B is Vm 10 minus 0.7 over R sub B, and that's 9.3 divided by R sub B. So we have two unknowns here, R sub B and I sub B. So how do we get I sub B?
Ten, you would use just the voltage, the 10 minus 0.7 over RV, then you could put that to 9.3 over RV.
And your earlier analysis is that the circuit is in the active mode. So in some form we could use the I sub C to find I sub B, and that's the equation here. I sub C is beta I sub B, and beta is, if it's given as 100, we can solve for I sub C is beta times Vm minus the base voltage divided by R sub B, and I sub C would be the current through the LED, basically. So we have the LED is requiring is 30 milliamperes, beta is 100, and now we only have one unknown, which is R sub B. So R sub B is around 31 k ohms. So if we build a circuit on the breadboard, it will work. When the op-amp output goes high, the LED will turn on. And when the op-amp goes low, the LED will turn off. So there's no contradictions to this circuit. Now this second version, and we put an LED in the emitter for no real obvious reason here. And we're going to still have a base resistor here. So when the 10 volts appears on the output of the op-amp, how do we get 2.2 volts on the base of the BJT? So we got 1.5, the LED, if the base emitter is on, the LED will be on, and about 1.5 volts, and then we add 0.5 volts across the base emitter. And that gives 2.2 volts on the base. So if there's any active mode, the LED is on with 1.5 volts, and the base voltage is the emitter, 1.5 plus 0.7, which is 2.2 volts. Now the same equation is going to apply here. The base current is Vn minus the base voltage over RV, and the new V sub B is VBE minus the LED turn on voltage. So that's 10 minus 2.2 over RV, which is 7.8 over the base resistor. And then we can convert our I sub C for beta I sub B. We can do the same. We have RV, and over here we have I sub C. Convert I sub B in terms of I sub C at the bottom. And we get the same equation as before, except this term here is just the base emitter minus is at 2.2 voltage here. And now we only have one unknown. We put 30 milliamps in for the electric current. And the math comes out to be around 26 k ohms. And it's the active mode. I check the active mode again. The collector is 10 volts. The base is 2.2, and the emitter is 1.5. So both of those p-n junctions satisfy the active mode. The DC collector emitter voltage here is above 0.2, so there's no, the transistor apparently is not saturating when it basically turns on the LED. Now the third these two circuits here, the first one, this is the turn on the LED, and then this is the I sub C in the first scheme. There. And then the second, well, before moving over to the second one, we find that the collector current in the first circuit is very dependent upon the beta of the transistor. And we did not spend much with the physics of the transistor network. What's the atomic structure inside the transistor to give beta? The beta can vary from 30, let's say, to 500. So that means the collector current here can vary a large amount directly with the transistor beta. So if we're trying to build 1,000 of these simple circuits, so we're putting them in a toy, and it's really just a light that turns on and off. There will be statistically there'll be a lot of these toys that do not work properly because beta, trying to sort beta in manufacturing can be very expensive. You need a robot, you need the computers, you need the test equipment, and then we need the manufacturing time to actually do the test of beta. So sorting beta is definitely would be frowned upon in manufacturing. Now, if the toy were very expensive, then you would probably go through and sort the beta. But another engineer would just say, well, better try a different circuit, so maybe there's a way to remove this beta dependency. So, the assessment of scheme A and scheme C, if beta varies 20% here, that's 120 instead of 100, the LED current will vary by 20% also. So instead of 30%, it's going to vary, instead of 30 milliamps, it's going to vary by 20%. And it turns out the second circuit, this scheme also has a beta dependency on the collector current. So neither one of these would be a manufacturable circuit. It would work as a hobby circuit, but if you're building hundreds of them, there would be failures due to the beta effect. So the remaining circuit, there's one remaining circuit, and the key to the remaining circuit is to check whether we get the same type of beta variation when we build the circuit. And if we do, then that means we have 3 circuits that do not work, and now we have to go off and find a 4th version. So this version here, this is the second scheme. This is where we put the LED in the collector, and it's not so much we put the LED in the collector, what we add is a resistor in the emitter transistor. This resistor, RE, this is called a degenerative resistor. And we can calculate the emitter current, which is simply the emitter voltage over that resistor. So that's equal to beta plus 1 times I sub B. Everyone's familiar with that, how to convert in that formula. And then in the formula at the bottom, our base current is still Vn minus V sub B over RB. And for V sub B now, we have I sub B RE minus 0.7 volts on the emitter. And what this converts into is I sub B is equal to I sub B over beta plus 1. So that's one. So at this point, we haven't come across a formula that's, the only formula that's multiplied by beta is I sub E up here, but that's the normal active node. So So we haven't come across a formula that is very dependent on beta at this point. Now, we can do an analysis of the base emitter loop. Do an analysis of the voltage drop in the base emitter loop here. And you can write it out on paper. However, it basically goes up to this equation here. Go ahead and solve this equation for I sub E. Paper. Just solve it. And you're solving it here so you won't have to solve for it on the exam. And you have I sub E in two places here. So we have to factor out IE, RE, and then combine it with I sub E. The lower part here, the note is the solution of this equation is an important formula that will be used a lot later in the course. So it's basically indicating solving the formula for I sub E is an important part of DJT. Everyone have your own version of I sub E. This is now if your version looks similar or the same as this, then you obviously have the correct result here. And this equation, in the denominator, you have R sub E plus RB over beta plus 1. Now, is this equation beta dependent? You might say it's moderately beta dependent. Beta appears in the denominator, and then it also appears in the denominator of R sub B. R sub B is usually a large kilo ohm resistor, and then beta is the second go from 30, say, to 300 or 500. So at this point, the equation for the emitter current does not show a beta. If there had been a beta in parentheses here, then we'd have the same problem with the other two circuits. So here's our formula to solve I sub E. Basically, we were given a circuit similar to this schematic, which is here. So now the design of it now, it means that now the designer using this circuit has to design two resistors, either RB and then RE. So the circuit is going to be a little more complicated to design. And we note here, there are infinitely many combinations of RE and RD that will give the desired ISO-E value. So if we want ISO-E equals 30 milliamps here is the infinite number of RE combinations that will give the 30 milliamperes. So how do we decide which is the best RD and RE combination? It's now the design question. Now, when we get into design, especially something that says there's infinite number of selections here, we basically want to use some mathematics to reduce the number of combinations. And one combination we can use is we can make RE much greater than RD over beta plus 1, or RE much less than RD over beta plus 1. And that's going to reduce the infinite number of combinations down to a lot smaller group of numbers. So if you try the first one, make RE much greater than RD over beta plus 1. There's still lots of combinations that will meet that. So you would probably take out an Excel sheet, program the formula, and then just go through arbitrary values to come up with a combination that appears to work. And if we can get the right combination, then this will give us what's called weak beta dependency in the circuit. Because this circuit, it doesn't have a multiplier of beta, it does have beta in this part of the formula. So we want to get an RE and an RB that give us weak beta dependency. So here's the same problem before. IE is 30 milliamp. And if we solve this based on ISO-E only, we come up with this RE, this formula is equal to 0.31 K ohm itself. So you have two unknowns here, and you have to make up decide on some number for each one of them. So if you decide, let's say we try RE is 250. Remember, there's hundreds and hundreds of combinations. So you obviously would not pick RE equal to 10 megohm. And why is that? You definitely would not put a 10 megohm resistor here. Why is that?
Too much resistance?
You need another very
It would go in the cutoff.
oh, good.
There's no current flow. So large resistors don't work, so you decide, well, let's go to the other side, and we'll start with smaller resistors. So this one says, let's try 250 ohms for RE. And now we have an equation with one unknown, and we solve it for RB. And beta is 100, get RB is equal to 6 K ohm. And now we can go in and test the weak beta dependency theory here. So if beta goes from 100 to 120, which is a 20% change, the emitter current changes from 30 milliamp to 31 milliamp, and that's a 3.3% change in emitter current for a beta change of 20%. Now, if you're the engineer being responsible for making hundreds of these circuits, so you're you would basically go to, probably you visit the foundry. You need a plane trip probably over to where the foundry is at, and you would get to the engineers, manufacturing engineers that make these transistors, and then you would start going over the statistics data to get a better idea of what's going to happen with beta, worst case beta, and then nominal, and then best case beta. And then you would use that to, like this is just an arbitrary beta goes from 100 to 120. What if your real was beta changed by 50% or something? And you basically decide I'm going to keep that as a worst case for this design to come out the axis scale for it. So far, the circuit appears to work with these combinations. And then active mode check over here, the emitter is 7.5. And on an exam, when it says to check the active mode, this is basically, other than VC, E stat, these are the three numbers that you're checking. The emitter voltage is 7.5 here. The base voltage is 8. The collector voltage 10 minus 1.5, which is equal to 8.5. So this basically confirms the active mode. So this is a usable circuit. Now the other part of manufacturing this circuit would be the LED is going to have a variation in its turn-on voltage. So you probably research the LED foundry and get their PN junction variation. And there's also temperature and other parameters. We're just assuming whatever happens, it's only beta that we're concerned about. So this point here, and I'd say we're still working on the circuit. So now we decide to try a different RE. And this one is 280 ohm. And that's not much different from the 250. So we try a different one, and we calculate a new R sub D, which is now equal to 3 K ohm. Now, would you predict that the variation in emitter current is going to be better or worse with this change? You only have 30 ohm change in the emitter resistor. The problem is the base resistor has dropped from 6K to 3K ohm. So in the circuit now, so this combination, again, because the base resistor is smaller, and according to this ISO-D formula, it means this RD is going to get smaller, and depending on the direction the beta goes, this side of the equation is going to get similar to R sub E. So R sub E and beta and RB are basically moving towards each other. So rather than kind of guess at it, you decide to just put it in the formulas and try it. So here, if beta changes 20% again, and you change the resistor to 280 ohm, now you find that the emitter current only changes by 0.5 milliamp, which is only 1.67%. So is that an improvement? The first combination gave 3.3%, and now this is 1.67%. So we would say, well, that's an improvement. However, what's happening is the circuit is introducing another property, and that's what's called the Rn of the transistor. That's the resistance looking into the base of the transistor. If the RB gets too small, then you develop a loss on the input before you even get to the transistor. So although this looks more promising, it basically may be introducing a problem with the RN. We'll get to RN when we basically look at common emitter amplifiers, but at least on paper, this is saying that changing that resistor 280 ohm, changing RD to 3K, we get the beta change to 1.67, and then going back and checking active mode. What's the status of the active mode check now? Before we send the circuit to build hundreds and manufacture it, we decide, let's check the active mode. So is the active mode okay for this design?
Yes.
So on paper, that resistor change gave a improvement. However, when we went to build one of the circuits on a breadboard, we found out that the circuit didn't work. The LED would not turn on. And then we checked the active mode numbers. The emitter is 8.4 volts. And we can calculate that. The emitter resistor is 280 ohms, so you can calculate that number. The base voltage is 9.1 volts, and the collector is 8.5. So I'd say part of your homework is to check these numbers here, because this is the nightmare that basically results from not checking what appears to be a relatively okay design. So what's the problem with the active mode numbers?
Too close.
The
base voltage of 9.1 is greater than the collector voltage of 8.5. And the other problem, the emitter voltage is 8.4 and the collector voltage is 8.5. So DC stat will equal to 0.1. This transistor will be in saturation. And it would not switch the LED on and on. So this design, this over-design basically would cause the problem of reducing RN, and it also pushes the transistor out of the active mode. So the X goes in there and just says that this is not the best route to take. Now a 200, you take a 250 ohm resistor, if that's a 5% resistor, what's 5% of 250?
5%.
10?
10 ohm?
1.15.
5%.
What is it?
1.15.
5% of 250.
Oh, 25 to 13.
No.
12.
5 times 25.
12.5. 12.5.
So it's somewhere between 10 and 15.
Yeah.
10 and 10. And that, so if you bought 5% resistance, this could go from 250 to 260, and you're moving toward saturation. Which means basically goes back and says this design is basically very sensitive to your choice of RV and RE. But this new version would not be acceptable. So the second scheme B is definitely better than the first and the third A and C. The larger RE from RV of the beta plus 1, the weaker is the beta dependency. Remember, we only tried two versions of RE and RV. That's why I was going to send you to take a spreadsheet and go through many versions and try to find an optimum combination for the circuit. If the BJT saturates, you no longer can drive the required DC current. The LED would not function, and there's a limit to how weak beta dependency can be. And this is not bringing in temperature and other parameters in the circuit. So the summary, an op-amp has limited output capability for driving loads that require lots of current. A BJT can usually drive current, even up into the ampere of current. And when you use the NPN to drive current, it goes from the collector to the emitter. Now, if we did the same analysis with a PMP, we basically should come across the same results. So they just have the direction of the currents would be different. And another question is, what happens if we need to, we kind of go back, that last question is asking, in this design here, the current is always in this direction. And what if we needed a design that could operate with current in both directions? When current flows in, it works, and when current flows out, it still works. This is saying what happens if we put an AC signal on the input instead of DC. An AC would reverse current, and then the transistor would turn on. So the circuit won't work with AC, in other words. Now, so this last part of the design is indicating that there's still an advanced version of this circuit, and that we need to add another BJT to actually accommodate the dual polarity of the AC. And we will see that in our next session. Now under the problem set section on the modules, Dr. Moss has a section, BJT DC current driver and BJT DC circuit. And these are from some earlier quiz. So this version here, it shows a PMP transistor, and PMP in their base is 0.7 volts when the base is 4.5, base 100. Whenever BJT is in active mode, the VC EC set is 0.1 when it's in saturation. So find RV so the BJT is in the active mode with I sub C equal to 2 milliamps. So how do we, given the schematic, and so the question said find this resistor in the base that will cause I sub C proceed to be 2 milliamp, and the transistor will remain in the active mode. So how would we proceed? It's not much information given, however, it is enough information to solve the problem. We notice our RB is grounded, which is fine. We don't need DC voltage on a PNP transistor. It's grounded based on the PNP.
So you have the voltage at the base is equal to 0.7. So
Okay, what's the voltage at the base here?
voltage increase 4.3.
Right, so the emitter base of the PNP is 0.7.
0.7.
So the base would be 5 volts minus 0.7, 4.3. And then we have a base voltage of
0.
4.3, and the current is 4.3 divided by I sub D. RD, that's going to give us I sub B, and then we can use the collector current to manage the I sub B over here and eventually calculate the R sub B resistance. So, in the analysis then, the emitter is 5 volts, the base is 5 volts minus 0.7, which is 4.3. The base current is I sub C over beta because we assume active mode, so we have 0.02 milliamp through R sub B. And I sub B is V sub B over R sub B. You notice the two equations for I sub B are two versions of it. So I sub B is 4.3 volts over RB, and it's 4.3 volts because RB is connected to ground, so RB is 250 k ohm. And now, for PNP to check the active mode, the base is 4.3, the collector is 0. Is that okay for PNP? PNP, the collector voltage is less than the base voltage. So that combination is okay. And we already established this 0.7 volts across emitter to base, so that basically takes care of the emitter base junction. So yes, it is in the active mode. And the lower part of it is asking what happens if you change the battery to minus 5 volts? We kind of go through the concept before we try to do a tape analysis. If the emitter is now 5 minus 5 volts, and
base voltage.
we still want 2 milliamp to flow from the emitter to the collector. So we still want this current flow direction. So there's something unusual about that because this lower terminal is ground. So we want current to flow from minus 5 volts to ground. Is that okay?
No.
We're going to go from a negative battery to ground. There's something about that direction is not working here. But we still proceed until we find a contradiction, though. That's maybe a contradiction, but it's not really enough. So if we have minus 5 volts on the emitter, what's the voltage on the base?
Negative 5.7.
Negative
5.7.
Negative 5.7 on the base.
But that's the contradiction.
And then we have a negative now
Collector.
we go, the collector is
Zero.
zero. Now the base is minus 5.7, so we come across another contradiction in the active mode. That means the collector voltage is greater than the base voltage on the PNP. So we have to kind of put together what does it all result in. And it's not no longer an active mode, it's most likely not in saturation. However, we basically go through the analysis assuming active mode failed here, and it's not in saturation because the current is going backwards. So the only mode left we can declare is we're going to assume cutoff mode for the circuit. But we really can't find a logical result for active mode or saturation. So we assume cutoff. Emitter current is equal to collector current or base current, both zero. And the assumption that the base is at minus 5.7 means current is flowing in the wrong direction. That means this diode is biased in the opposite direction. That means there's no voltage on the base, so I sub B is equal to zero. And if I sub B is zero, the base emitter junction, the emitter is less than the base, that's the one we found before, minus 5 volts less than zero, that's reverse bias. The base collector junction, base collector is B sub B equal to, and this is reverse bias also. So the collector is already grounded, the base is grounded, so the base collector junction are both zero, and that means there's reverse bias on the base collector and reverse bias on the base emitter. So I sub C is equal to zero. Now, a problem like this, it's fairly straightforward if we're basically understanding it's a PNP device. And if this had been an NPN transistor, basically, the analysis would definitely be kind of more simplified. But because of the PNP, one of the requirements for PNP being cut off, if both of the PN junctions must be in reverse bias. So you come across a problem like this, and there might be a problem in homework 2 similar to this, but it's asking something about cutoff. So you want to be aware in order to prove cutoff, we have to get the voltages on each terminal of the VJT, and then from that, study whether the PN junctions are in forward or reverse mode. And this is an LED problem with 2 LEDs, one in the collector and also another one in the emitter. So the battery is 10 volts and it's saying the base voltage is 5 volts. We want the DJ to be in the active mode, and we want the current I sub C, I sub E equals 20 milliampere. Find R sub D and verify the VJT is in the active mode. I believe one of the problems in homework 2 does have an LED component. So, what is the voltage on the collector with 10 volts on the battery? 8.5. 8.5. And what is the voltage on the emitter?
1.5.
1.5. And then what's the voltage on the base?
VPB minus PC.
So 1.5 volts on the emitter, if it's an active mode,
So this, it's gonna be 2.2.
we got 0.7 to 2.2. And now because VBB has given us 5 volts, we can solve for R sub B and notify BJT, find RV and verify it's in the active mode. So we kind of go through the way we're looking at these problems is that you want to kind of reduce the tendency to produce multiple results for a problem. When you get into that multiple results, you know, a 5-minute problem turns into a 15-minute problem because now you've got to investigate each one of those results. So before solving a problem with BJTs, kind of study the circuit and kind of come up with a logical method to actually work with it. And that way you don't have to get into diodes, which are on and off. Diodes definitely, if you take a pattern with diodes and you try to solve different versions of it, you know, one of the versions will work. But it's just the time that it takes to go through those steps. BJTs are somewhat more straightforward because they have 3 different modes that they operate in. So on paper, for your homework, go through this, and also you're working on homework too, so you can kind of introduce to that. So the author here is drawing some currents on it, current flows from the collector to the emitter. And so the emitter voltage is the LED 1.5. The base is the emitter plus 0.7, 2.2. The collector is the battery 10 minus 1.5, 8.5. The collector voltage is greater than the base voltage. That's active mode. I sub V is I sub C over beta. I sub C is 20 milliamp over 100.2 milliamp. And then RV is the 5-volt battery minus 2.2 volts on the base over IV. And then divide that by the 0.2 milliamp, we get 14 K. So this problem is it's more likely a 5-minute or less type problem. The idea is that by studying the problem first, we can kind of produce a pattern that's going to probably lead to a result that kind of makes sense logically. It would not be logical to assume cutoff or saturation in the circuit. Maybe. But if we do run into saturation, of course you basically have to reverse and go back to something else. Now this is the it's pretty much the same problem replaced by a PN transistor, which means the current directions and the voltages are going to be opposite from the NPN. Now, you can basically take the NPN and try to reproduce it. So, what's the voltage on the emitter here? 10 minus, and we note because we don't want to overlook if a problem appears with the LED in the opposite polarity, and then the transistor would be cut off. And now we're going to spend 15 minutes and finally realize the LED was actually backwards. So the LEDs apparently, current should flow from the battery to ground. The LEDs appear to be in the right polarity, so the emitter here will be 10 minus 1.5. The collector, now what would be the collector voltage? Would it still be 1.5? Now, knowing the collector is helpful. It's not going to help much in finding RV, but the emitter, so what's our emitter voltage here?
Sure.
The 8.5 minus 0.7.
Oh, 7.7.
And then the DB battery is 5 volts. So pretty much you're coming with the same type of result for the as you got for the NCN. And now notes here, even though the math for the PNP is different, it's coincident that the both results are the same. They should be the same, because we assume that PN junction, PNP is 0.7, and this problem is saying, consider this circuit. I sub C is 5 milliamp. The battery is 9 volts. The resistor R sub C is 2K. And we want I sub C to be weakly beta dependent. What does this term mean here? We just went over with weakly beta dependent. The author kind of leads to what is expected. Suggest reasonable resistor values RD and RE. Explain why do you think that these are reasonable. So what formula do we come up with first? IE is, now get that formula, how many RB, RE combinations are there? It's an infinite, so how are you going to start the problem?
IE is equal to Vn minus VDE over
What do you do?
RE.
It says select reasonable values for RD and RE. Megohms are not reasonable resistors, so we stay away from those. 100 K ohms are not reasonable resistors. We stay out of that group. And now, again, that leaves a large number of combinations. So, for your homework assignment, go through this problem. We could go through the author's results here, except it's a good idea for ourselves to get in position where now you've got to select two resistors, you've got to calculate the improvement or the not so much improvement with the change in emitter current as beta changes, and then you'll come up with your combination. So you decided, I know that RE equal 30K, not such a good number. And the reason is because for RE equal 30K, RB is going to be an unusual number. The circuit may not work. So again, you can work on this type of problem somewhere. We'll return our exams on our next session, and the grades will be posted on Canvas before that, and then we'll briefly go over